So now let's do part B, where we're supposed to revolve around the line y equals 2. So what's that going to look like? So here's our same region that we have with the y equals x squared and the y equals 1. But we're revolving around this axis y equals 2. So how's that going to change the shape? Well, basically, we can do a reflection over the line y equals 2 instead of over the x or y axis. We can just do a reflection over that line. I'm trying to keep it more or less symmetrical, but I had to squinch it in a little bit under my text. Yeah, that looks not too bad. Okay, now what you got to remember, though, is that this thing is revolved around this axis. So it's like got an open, this is an open hole right there, and it's open over here. All right, but at the same time, like the outer rim is just like revolved all the way around. So what you have is like this. Yeah, I'm lost on describing this one or drawing it. But basically it's like it's got a bowl-shaped outside, but it's got a cylindrical hole bored through the middle. I think it didn't help that this didn't quite line up here. Yeah, sort of like that. So maybe if I could do some kind of a rough side sketch, it's like this, like, no, this is definitely not going to help. Like this. And there's like a hole through the middle. So then there's maybe like an outer ring like that, and there's a hole through the middle. That's kind of almost it. This is like a nut with a hole drilled through the middle. Yeah, I think maybe this needs like an outside part to it. So it's sort of this round bowl with a hole drilled through the middle. So you can probably sort of imagine that better than I can draw it. Anyway, it's like a poofy washer. All right, so fortunately, in order to find the volume, we don't really have to draw it well, although what might be helpful is to have just the cross-sectional area drawn in, because that'll help us see how we're going to analyze it. So in this case, we're going to have, the question is always, what does your ith volume element look like? So here's our ith volume element is like this. So when I revolve it, it's going to form a washer. So I'm going to have washers. I'm, again, just doing the cutaway version of the washer. So I only have half of it. All right, so that's my V sub I right there. So if I look at that, I can pull it out and say, what I've really got is a washer. It's got a hole. Right. And I've really, of course, got a number of those going around through here, and they get smaller over here, they get bigger, but the inside is always the same. All right, so that's my V sub I. So my V sub I, as always for a washer, is going to be pi r squared minus r squared, the big radius minus the small radius. And since I'm parallel, my slices are parallel to the y-axis, this is delta x. And so my width here is delta x. All right. So then, the question is, what are big R and little r? What are they? So here's my axis going through the middle, and little r is the distance from y equals 2 to this line up here, which maybe it will make more sense if, again, I go, look at the radius at the bottom. So it's the distance from this y equals 2 to that top line y equals 1. So now what I want to understand is that top line is acting like a function f of x, and the bottom line is acting like a g of x. So these f of x and g of x are forming the boundary of the shape. F of x on the top, g of x on the bottom. F of x is just equal to 1, g of x is equal to x squared. And they form the top and the bottom of this. All right, so the small radius is the distance from the axis of rotation to the innermost function. So it's really, in this case, the top function is the smaller radius because the axis is up here. And then the larger r is going from the axis down to the shape itself. So this is the larger r. So the little r, all right, little r is going to be, just to write clearly, it's 2 minus 1, right? And then big R is 2 minus x squared. Right? So that's what my two radii are. So then, when I go to write the integral, I can sub those into here and here. Right, so essentially I could say at this point even that my v sub I, and I'll sort of write it out fairly expansively, is my big R, which is 2 minus x squared, but you know, I'm going to write x squared minus 2 again. Squared, because R is squared, minus my little r, which is 2 minus 1, but I'm going to write 1 minus 2 squared. Remember, I can reverse the order so that, because I'm squaring the quantity, and then that's going to be delta x. All right, so that's my ith volume element. So that means that my volume for this one is going to be the integral. So again, I'm going from -1 to 1. My limits are x coordinates because I'm integrating with respect to x. I know that because I have delta x here. All right, so integral -1 to 1 of this stuff. Well, let's put the pi outside, right? Here's our pi. Let's put it out there. And then I have x squared minus 2 squared minus 1 minus 2 squared dx. All right, so now I can probably sort of reveal why I keep reversing these. So because we could talk about the general case where I'm revolving around an axis y equals k. All right, and then what I would have here is my outermost function, the x squared, the g of x. So what I have here is g of x minus k squared, and what I have here is f of x minus k squared, where f of x is the innermost function. So this will give us an opportunity to formalize that for our next set of problems. Let's see, what are we going to do now? Oh, so now let's take advantage of symmetry again. All right, so this figure is symmetric with respect to the y-axis. So instead of going from -1 to 1, let's integrate from 0 to 1 and then double it, because the part from -1 to 0 is going to be the same. So we're going to call this 2 pi times the integral from 0 to 1. All right, and then we'll just square stuff out. So the rest of it, you can handle the rest of it easily enough. This should actually be x fourth minus 4x squared plus 4 minus, so this is going to be 1 squared, so it's going to be 1. I mean, it's -1 squared. That's going to be 1 dx. All right, so I have 2 pi integral 0 to 1 x fourth minus 4x squared plus 3 dx. So I have 2 pi x fifth over 5 minus 4x cubed over 3 plus 3x. We're going from 0 to 1. I won't bother to plug in the 0. We'll just plug in the 1. So I'm going to have 2 pi times 1/5 minus 4/3 plus 3 equals, okay? And then, you know, like, do these fractions. We're going to cross multiply. So it's going to be 3/15 minus 20/15, -17/15 plus 45/15 is going to give you 22/15. And then I have times the 2 pi. So I have 2 pi times 22/15. So that equals 44 pi over 15, and that's that one. All right, so for the next one, what we're going to do is try and formalize a little bit what we did here and what we did here, so that we don't have to go through this every time. It's good to be aware of this. We don't need to go through it every time. We want to be able to sort of jump right to the integral, as long as we know what integral we're jumping to and why, so that we could also create an integral for a function we've never seen before. All right, and so we'll do that, and we'll do part C in the next video.